it's working. And make sure sure my microphone's plugged in this time. Hey. All right. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to just bless this class, help us to understand a little bit more about your creation, about inverse functions, and just also pray that you'd encourage the students if they're struggling, just to do their best, Lord, and to leave the rest to you, Lord. In your name I pray. Amen. So, let's see here. I got a question for you. Test, whatever. Let's see here. Can you decide whether or not the following are inverse functions? So example 1, you've got f of x equal to, I don't know, x cubed plus 2, and you have g of x equal to the cube root of x minus 2. Are these inverse functions? Oh well, I was trying to go off the bounce. I heard yes, that's nice, but I guess my second question would be example 2. Let's look at f of x equal to x squared. This time I'll do minus 3, and no, x plus 3, yeah, and then g of x equal to the square root of x minus 3. Are these inverse functions? And so we'll look at these. So, I mean, yes, that's a lovely sentiment, but how do we actually check that they're actually inverse functions? What do we have to show? We have to show that they satisfy the definition. So to check that, remember the definition was that f of f inverse of x equals to x, and f inverse of f of x is equal to x, right? We need both of those things to be true for it to be the inverse function. So we need to check if that's actually true for the g or not, right? So let's try it out. F of g of x, what's that give us? So I think a nice way to think about that is it's like f of g. So put g in the place of x, and that's g cubed plus 2, right? But g is what? G is really the cube root of x minus 2. You got to cube that thing and add 2. Well, okay, well the cube root cubed is just the thing inside the root again. So that's x minus 2 plus 2, which is x. So looking good for whoever guessed that they were inverses, right? But this is just half of it. We need both. You need both to be true in order to get that it's the inverse. So let's check the other one. G of f of x, what's that? How's that work out? That's like g of f, right? My g was the cube root, rather, of g minus 2, of f minus 2, I think I should do here. Right, because that's the formula for g. We take the cube root of whatever goes into it, minus 2. But f is what? F is x cubed plus 2. So I got myself a cube root of x cubed plus 2 minus 2. Well, the plus 2 minus 2 cancels out, and I'm back to just the cube root of x cubed. Lo and behold, cube root of x cubed is x. So, hooray, you were correct. Indeed, the inverse of f, thus g of x does in fact equal f inverse of x. It is the inverse function, right? Is it surprising that an inverse function for f exists? I mean, my question to you is f a one-to-one function? What do you guys think? What's the graph of f look like here? So the instructions here it was just a question, right? Question, is g equal to the inverse function of f? That was the whole question here, okay? The question for the next example is the same. is g, the inverse function of f. Let's work it out, yeah? Does it work? Well, let's try. Well, let's look at f of g of x. What do we got? F of g, right? Which would be g squared plus 3, which would be the square root of x minus 3, parentheses, squared plus 3. Now, if I take the square root of something and I square it, I get back the thing inside the square root, essentially by definition. So this is just x minus 3 plus 3 again, which is x. Well, that's good. So there's half of it. How about the other? G of f of x. So I can look at that as g of f, right? Where my g is, what was it? Square root of something minus 3, so square root of f minus 3. My f was x squared plus 3, right? So I've got x squared plus 3 minus 3. The 3 and the minus 3 cancel, and we're left with the square root of x squared, which is what? It is not just x. Why? It's plus or minus x, right? So technically, this is the absolute value of x. This is actually not surprising. Let's contrast these two problems. So example 1, if you graph f, what's it look like? What's the graph? It's a snake, right? A sneaky snake. It's an S. It's got a y-intercept of 2, and it's one of these deals, right? And if you wanted to graph the inverse function, it's the cube root function shifted 2 to the right, right? So it's like basically notice that the y-intercept of 0, 2 has shifted over to a corresponding x-intercept of 2, 0, right? But the larger story here is that the red graph, the given graph, y equals f of x, it passes the horizontal line test, right? So the fact that an inverse function exists seems plausible. That doesn't prove that the given g is actually its inverse, but these calculations do prove that, right? Or graphically, if you like, you can see that g is the inverse. See, because g of x, the graph of g of x, it's precisely the reflection of the red graph across the line y equals x, right? If you mirror the I think that crosses there, but if you mirror this line here, this flips over to that, across that line. Now, let's look at example 2. What's the graph y equals f of x look like there? It's a parabola, right? And it has a y-intercept of 3. Right? If you just mirror that shape, if you trade x for y, what you have is not the graph of a function. You actually have this. That's not a function.
What is it?
It's a relation. Welcome to Math 200. Anyway, yeah, but anyway, now I'm just getting more back to the point here. So y equals x squared plus 3, right? That's my f of x. It clearly fails the what? Not the vertical line test, but the horizontal line test. which means its reflection will fail the vertical line test. And if the reflection fails the vertical line test, it's not even a function. That's why one-to-one functions have to, that's why an invertible function has to be one that the horizontal line test has to pass for horizontal line test, because otherwise when you reflect the shape across the line y equals x, you'd have something that doesn't pass the vertical line test. It's another way to understand things. There's this duality. But, okay, so in other words, is G equal to F inverse? The answer is no, because F is not invertible. Yeah.
So basically, any sort of polynomial with an even subscript would be
Not invertible?
yeah.
Any even polynomial is not invertible. Yeah, I think that's probably true. Not without adding fine print. Like, it's easy enough to fix. Check this out. So if we do f of x equal to x squared plus 3, and we say that the domain of f is 0 to infinity, then we fixed it. See, because we can have g of x the same as I did. The algebra works out exactly the same algebra. So we still have, but what's the difference? Yeah, f of g of x. We have to test this equation for every x in the domain of g. And this one still works out to x, that's fine. But g of f of x, that's the interesting one. That's absolute value of x. But the domain of f is this, right? So this is equal to x for x in the domain. And so yes, they're inverse functions. And graphically, we can also understand this because by chopping off half of the domain, we fixed the problem that was there before. See, now rather than having the whole sorry, just a moment of stupidity. So here's my graph, right? For f of x. Now it's just half of the parabola by our definition. I just ruled out the other half by fiat, right? So and then the graph of the other one is just the same thing, but turned sideways. So it's an interesting and difficult question to ask. Given a function, how can you restrict it to make it invertible? That's a question I don't ask you guys, but you might be asked it in like the end of pre-calculus, because when we talk about trigonometric functions and the inverse of trigonometric functions, this idea of restricting the function so that the domain becomes smaller and it's invertible, it comes back up again, and you can't ignore it. It's not like a side topic in trigonometry. It's a central topic, because to understand the buttons on your calculator, like inverse sine, inverse cosine, inverse tangent, it must be understood through the lens of restricting sine and cosine tangent. All right, enough about that. We had a theorem last time. What was the theorem? I'll state the theorem again, which is this, right? AB in graph of f, then BA in graph of the inverse function. So how is that? How do you prove that? Well, what does it mean for AB in the graph of f? That means that B is equal to f of A, right? For A comma B to be in the graph, that means you get the y component by taking f of the x component, right? So what happens if we take f inverse of this? So if we take f inverse of B, we get f inverse of f of A, right? And f inverse of f of A is by definition A again. So we have that A is equal to f inverse of B, and this means that the point B comma A is in the graph of F inverse. So I don't prove too much in here. I just wanted to point out to you that this theorem that if A comma B is in the graph of the function, then B comma A is in the graph of the inverse. It's not a terribly deep theorem. Really all it's saying is apply the definition of inverse function to the meaning of graph. That's all it is, okay? The more important thing here is we can sort of kind of organize our thinking tabularly like this. You got F, you've got F inverse, right? If you've got a horizontal asymptote over here, you get a vertical asymptote over there. If you got a vertical asymptote here, you get a horizontal asymptote over there. If you've got an x-intercept over here, you get a corresponding y-intercept over there. If you've got a y-intercept over here, you get an x-intercept over here. There's this duality. We flip horizontal asymptotes to vertical asymptotes and vice versa. We already just saw this duality in play over here, right? My y-intercept of, what was it? 0, 3, flipped to a x-intercept of 3, 0. All right. Let's try this theorem out on a more concrete example here. So suppose you're given a function, all right, and I'll make that function look like this. So we'll start with minus 4, minus 1, and then I'll go over here to, looks like maybe 4 comma 1, and then I'll let it go up here to, let's say, 2 comma, use your, that's a good question. Thank you. 5. It's like 6. Fine. I can compromise. 6, there you go. 6, and let's see here. If that's 4, it's probably 5. All right. And I'm going to connect the dots, yeah? So here you're given y equals f of x as pictured, all right? Then the question is, what's the graph of the inverse function? And I would add, can we talk about the domain and range of both? We can do that, right? Like, let's start out with what's the domain and range of f before we do anything else. Can you guys tell me that? Domain is minus 4 to 6. And the range is what? Minus the range of f, minus 1 to 5. Okay, yeah, I'll buy it. Sure. Now let's graph the inverse. What's the inverse graph look like? So we do what? Let's start out with this point. We go minus 1, minus 1, 4, right? So this and then down here. Excuse, I'm an idiot. Minus 1 comma minus 4. My bad. Minus 1. It's a graph. So it's like here-ish. Sorry, it should be in quadrant. Still should be in quadrant 3, because it's still both coordinates are negative. Yeah, so it's down here.
Okay, so if they're positive, you keep them positive.
We don't flip any. We just flip the numbers. If they're positive, it's just literally flip-flop the numbers. There's no playing pluses and minuses there. Yeah. So 4, 1 flips to 1, 4. So goes up here, yeah. And 6, 5 flips to 5, 6. So it's like here-ish. To the limits of my artistry, of course. And then connect the dots. Because like geometrically, a line is going to reflect to a line. So I can expect that these lines fix geometrically what's going on here. So the red graph is y equals f inverse of x. And notice that we can see the domain and range for the inverse function, right? What are they?
The domain range of the inverse.
Yeah, what's the domain for the inverse? Yep. If you did it right, they better flip. If your range and domain don't have this interrelation, right? So these should match. Oh man, what did I just do?
You just have to put negative 4, 6. The graph is right. You just wrote it wrong.
Yeah, but he messed up.
Like the
Minus
top.
4, 6. Not minus 4, 5.
Yeah,
It's
the
minus 4,
range
6.
for your inverse should be 6 instead of 5.
Just in the class.
The black, the black,
Everybody go home.
range of the inverse should be negative 4, 6.
Oh yeah, right. 'Cause those are the y values of the inverse, the red line. Yeah. And there we go. Now those match, right? And likewise, the domain of the inverse function is the range of the function. There should always be this matching, right? Also, if there's any point on the graph of the function which crosses the line y equals x, what happens to that point? Like in this graph, if this is a line from minus 4, 1 to 4, 1, then one of the points you're crossing is the origin, right? So this point here on the origin, what happened to the origin point? Yeah, it just stays the same, right? So if you cross the line y equals x, that point will be fixed. It'll be a point both on the graph of the function and the inverse function. So, and then if if we did it right, you should be able to see that there's a symmetry of the two graphs about the line y equals x. You don't have to draw the line y equals x, but it's helpful to check. Shall we do another? Let us do another. Oh, before I do another, I should mention there is just a general pattern that we should notice about like the power function and the root function, right? So we do have, so if we have f of x equals x to the n, right? Then f inverse of x is equal to the nth root of x, provided n is odd. See, because we have that the nth root power, the nth root of x raised to the nth power is equal to x, and we have that the nth root taken to the nth power like that is equal to x. This is true for n odd.
is it not true for n even?
Because for n even, we have the following, but if n even, then we have that the nth root of x to the n power, well, that's still equal to x. But if we have the nth root of x to the n, it's equal to the absolute value of x. For example, like the square root of x squared is equal to the absolute value of x, or the fourth root of x to the fourth is equal to the absolute value of x, etc. So the power function and the root function are inverses only for odd roots. Otherwise, you got to be careful. You have to include the plus or minus when you take the root of both sides. If you take an even root of an equation, we have to assume, we have to allow for plus or minus. That's because, well, it's because the graphs are different, right? So for, this is y equals x to the 2k, right? This is y equals x to the 2k plus 1. That one fails the horizontal line test. It doesn't have an inverse. This one passes the horizontal line test. It has an inverse. That's the difference between the even and the odd root from the perspective of inverse functions.
Wait, which graph is even?
Which what?
Which graph is even?
Even.
Where's the bottom one?
This is odd. It's in, and I mean that in every sense of the phraseology. Like even as a function, as in f of minus x equals to f of x, even as a power, like 2k is an even power. This is an odd function. F of x is equal to minus f. I mean, f of minus x is equal to minus f of x, and it's also odd as a power. Odd power functions are odd functions. Even power functions are even functions. This is what the difference between example 1 and example 2 was. It's just the n equals 2 and n equals 3 case of this phenomena. All right, let's get back to my examples then of the graphical stuff. Example 5. So you're given y equals f of x, then graph y equals f inverse of x if possible. What's that? That means no? Here, I'll give you two choices. That way it's 50-50, yeah? So here's one. Whee! There you go. Let's see, I'll put some points on here to help us out. This point will be 7. Look what all right, 0, 3, let's say. And this point over here, we'll say is minus 2, 0, just to help us out. All right, anyway. So my question is, graph y equals f inverse of x if possible. I'm giving you both of these are y equals f of x, okay?
A is impossible.
A is impossible. Why? Fails the horizontal line test, right? So if we take this horizontal line right here, go beep, bop, fails horizontal line test. So that says not 1 to 1, thus F inverse does not exist. So we can only invert a function if it is a 1-to-1 function. That is not, therefore we cannot.
The other one you can.
The other one, yeah, the other one we can. So, so I'm not going to try to graph this one on the same axis because it gets too busy, yeah? What I want to put into practice, though, is this table. I want to put the table into practice. All right. So like I have a x equals -1 vertical asymptote.
You'd have a horizontal asymptote of 1.
Nope, there's no flipping plus and minus. We just change x to y. So we go y equals -1 instead. So y equals -1 is my new asymptote for the inverse function.
And then a vertical one.
X equal to 2. So what was a horizontal asymptote becomes a vertical asymptote. What was a vertical asymptote becomes a horizontal asymptote. That's the duality between the functions graph and the inverse function. This is the mirroring. And then, well, I can follow my points, right? I've got this point, -2, 0, so it becomes 0, -2. 0, -2 is like here, right? What was a x-intercept has now become a y-intercept. And I also have the point 0, 3. That was a y-intercept. It becomes an x-intercept of 3, 0. All right. And now let me introduce some color coding here just to make things easier to track. Instead of making that red, I'm going to make it blue. This hideous Carolina blue. But anyway, so that is this one, right? So apparently it does like that, right? This before vertical asymptote thing is becoming a horizontal asymptote thing, and this before horizontal is becoming vertical, if I do it right. And then the red piece, you know, this piece which was horizontal now becomes kind of vertical, and then this piece which was vertical becomes horizontal essentially. So there you go. This is the graph of y equals to f inverse of x. Now, if I try to graph those both on the same plot, it's hard to look at. All right, but let's do one more example in terms of this part of the inverse function material. Let's find the inverse here using formulas instead. Okay. Let's redo this example part B, but with formulas. So example 6. So I guess first thing we need to do is, what is a formula that has that graph? Can you guys tell me? Because that could have been a problem on the last test, right? Huh, oops.
X plus 2.
Well, I need an x plus 2 upstairs, right? Thank you. And I need a vertical asymptote at x plus 1, right? Yeah. And I need a horizontal asymptote of 2, so that means I need to take the top times 2. This has x-intercept minus 2, 0. It has a vertical asymptote, x equals to minus 1, and it has a horizontal asymptote of 2 over 1, which is what we have over here, right? Exhibit B, that's it, right?
No, still missing the y-intercept.
Meaning what?
The y-intercept.
The y-intercept? Well. That may or may not work. I don't know. Did I say 0.3? I meant 0.4. There we go.
4. Time out.
And let's see here.
I told you 7, man. She put 7.
There we go. I think we're okay now. Well, otherwise I have to think harder about it.
What was wrong with it?
If I plug in 0, I didn't get 3. If I plug 0 into this formula, I get 4 over 1, which is 4.
Oh, so this is for the
Yeah, I wanted to find a formula for that, but I think the fact of the matter is putting this point 1 unit above that horizontal asymptote and putting this one down here 2 units below the horizontal asymptote, both symmetrically 1 unit away from the vertical asymptote, means that I'm not dealing with a reciprocal function. That speaks to an asymmetry of the 2 branches of this thing on either side or the other of the vertical asymptote, which is to say that it's not a reciprocal function, which means it's something much more complicated to find, to map, to fit the data that I had here for the graph. I would need a much more complicated formula. Like, I don't know, like it would be 3rd order or something, much worse. So if I just change that to 0.4, then what that means is that these are symmetric and they're like interplay between the asymptotes, and so that's better. Because this is then 2 units from there, and this is also 2 units from there, and that's 1 unit, and this is also 1 unit. So I think it's
all proportional.
yeah, it's all proportional. Anyway, dang it. Ah, all right, now I'm behind. All right, so here we go. Y equals to 2 times x plus 2 over x plus 1. We're trying to find the formula using algebra now, okay? So we write y equals, that's step number 1. Step number 2, solve for x. So we've got x plus 1 times y is equal to 2x plus 4. Isolate your x's. Well, first of all, multiply this out. We've got xy plus y equals to 2x plus 4. Put all your x's on one side. We've got xy minus 2x is equal to 4 minus y. Sorry, my y's and 4's look so much alike. It is what it is. And then factor x out. And then divide. So my step 3 was to write f inverse of y equals the stuff in y. In this case, the stuff in y is 4 minus y divided by y minus 2. And then if I want to write the formula in x, I switch x to y to x at the very end. And so I get f inverse of x equals to 4 minus x over x minus 2. So that's how to do it algebraically. If you look at the graph of y equals f inverse of x, what are its quirks and features? X-intercept what? X equal, yeah, 4, 0, right? From the numerator, that's 0 when we put x equal to 4. Vertical asymptotes?
2.
X equals to 2, right? Horizontal asymptote? So we got a minus 1 over 1. So the horizontal asymptote is minus 1. And that, of course, is what we had over here, right? Horizontal asymptote of minus 1, vertical asymptote of 2, right? X-intercept of 4, 0. We've got all those things. Now, I'm personally a much bigger fan of the algebraic way of doing these kind of functions because, like, graphically, there's a pretty good chance you guys are going to get the graph wrong. It's about like 60-40 students are going to get this graph wrong. If I just say graph, if I tell you guys graph, you know, y equals 2 times x plus 2 over x plus 1, about half of you are going to give me very wrong things. But I do think that there's hope for this algebra. If you can be completely lost with graphing and you can still do this algebra, right? There's an algorithm here. You set y equal to the formula. You solve for x. That is what we call the inverse function then. And then switch y to x, and there's the inverse function formula. All right, so next up, we talk about a new kind of function for us in here. So we've talked about power functions. I'm erasing them right now. This is a power function, right? I'll keep it for my comment here, all right? F of x equals x to the n. This is a power function. Why? So the base is variable. The power here, n, is fixed. Right? So that makes it a power function. If the exponent is fixed, it's a power function. On the other hand, by definition, if we have something of the form a to the x, all right? Now here, the base is a. Is fixed, all right? And the exponent, the exponent is variable, right? So an exponential function has an exponent which is variable, and the base has to be a constant. I mean, it has to be exactly like this to be an exponential function, though, okay? It's not like I can't have x squared plus 3x minus 7 or something. That wouldn't, strictly speaking, be an exponential function. It would be the composition of an exponential function with a polynomial or something, okay? But this is literally an exponential function. And we haven't studied their properties yet. So a standard example I give that I think is helpful, y equals x squared versus y equals 2 to the x. Very much the same kind of formula, but very different. This is power function, graph of a power function, right? In fact, you know what that is. That's a parabola, right? We've studied that. This, on the other hand, is exponential. Exponential function, base 2. What does the graph of an exponential function look like, right? We don't know yet. Or maybe you know, but you're not allowed to know yet. Let's find out. So if we put x here, we put 2 to the x there, we can put some values in like, oh, I don't know, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3. Yeah, but they're easy enough. What is 2 to the minus 4 power? That's 1 over 2 to the 4th power, right? Also known as 1 over 16. So what you got here is 1/16, 1/8, 1/4, 1/2. One-fourth, 1/2. What's 2 to the 0 power? 1, right? That's good. Oftentimes students want to make 2 to the 0 equal to 0. which is not the case. 2 to the 0 is 1. 2 to the 1? 2. 2 to the 2? 4, 8, right? So now we can graph this thing. And so let's see here. So 1/2, quarter, an eighth, something like that, right? And it gets real big real fast. So this, of course, is known as exponential growth, right? Up and up and up. So then, great, this is y equals 2 to the x. Yeah?
That looks like the square root function.
It might appear like the square root, but that's just a quirk of my graphing. If you put them both on the same axis, you can see they're quite different if we graph them to scale. So is this an invertible function? Is it a one-to-one function? It is, right? So, definition. F inverse of x is what we call log base 2 of x. This is the inverse function to the 2 to the x function. In particular, it satisfies the following identities. Log base 2 of 2 to the power x is equal to x again, and 2 to the log base 2 of x is equal to x again. This is for any x, and this is only for x greater than 0. See, because the range of the 2 to the x function is the what? Range of 2 to the x is 0 to infinity, right? And that's the domain of its inverse. So we can only input a positive number into a logarithm. What's its graph look like? We just reflect this across the line. So 0, 1 becomes 1, 0. This horizontal asymptote becomes the vertical asymptote. And like that. So there you go. That's y equals log base 2 of x. Now, so like next class, I will define log base anything. And we'll look at what they look like graphically. I'll get the computer out to cheat for a bit. And we'll look at what their graphs look like. And then we'll talk about properties of logs and how to work with them, how to solve equations with them. All right? All kinds of things. So, but anyway, to understand this, we must first understand what's an inverse function. That's why we've been talking about inverse function. So anyway, that's it for today. I will now return your test to you guys. So you can hit stop on the record.